Hi everyone, my name is mpyanev, a professional software engineer and a computer science professor at Fitchburg State University. This is our first video on data communications and networking that took place at Fitchburg State University. We will talk about how messages are transmitted through a network, the different types of links, the devices that build a network, networking topologies. We're gonna briefly discuss all layers in the OSI model and much more. If you just came across to my channel or you're some of my existing students, please consider subscribing for more videos like this one. Now, let's not lose any more time and jump straight to the tutorial. Okay, so as I said, today we're just going to talk a little bit about what data communication is. We're going to talk about the network basics, so we'll speak about different links, topologies, those type of things. And after that, we're going to talk a little bit about the types of networks, an overview on how the internet is built from those networks, and also I will introduce you to the TCP/IP protocol. Okay? So, okay, let's get started. Okay. So, let's first review what actually data communication is, right? So, as you can see, firstly, we can start with the word communication. Communication is when we exchange information between each other, right? And just to mention one thing, everything that is surrounding us, whether it is vehicles or computers, everything it is built from the most basic principles that human has. So you can imagine that, you know, people are thinking, okay, we communicate between each other. Now, based on the different ways we're communicating in the different components of the verbal communication, how we can now build some communication from distance, how we can involve computers into that. So every creator of something new is using the most basic principles. And you'll see that when I start revealing what data communication is. So, obviously communication is when we exchange information. Telecommunication is when we exchange information from very big distance, right? So, these days we take this as something that we already have, but you can imagine in the past communication was extremely difficult. So even if the person is in the other building, there is no way for me to communicate with that person, right? Now it is way more simple, so we take it for granted. Data communication obviously means that we exchange some information and we call this information data, right? Pretty straightforward. So what are the different components when we are exchanging data? For example, when I speak to you. So first of all, when I speak, I'm delivering my message, which is the voice message that I give. I deliver it to you, right? So we need a sender, which in that case is me. Then you need your ears as a device to receive that message that I'm sending to you right now. So you're the receiver, okay? And here is the message wherever I exchange. Now, we also need a transmission medium. So when I'm speaking to you, what is the transmission medium? Air, right? Exactly. So if there is no air, and if there is no atmosphere, for example, if we're in the universe, am I going to be able to deliver this message to you? No, because in order for a signal to travel, you need some medium for this signal to travel. So if you're in space, there is no atmosphere, so the sound waves, they cannot reach your ears. Okay? So those are the four most important components when we want to exchange information. Now, there are a few criteria with which we can actually decide how successful is our communication, right? So the first one is delivery, right? So were there some delays when the sender wants to give the message to the receiver? Okay, how accurate was that? So let's say if I want to say something to you, but this message gets changed along the way, you might get a completely different message. Okay, so this is very important that exactly what I want to deliver to you actually gets delivered to you. In the same way, let's say if I want to send you a mail or the post, if somebody takes the mail, reads it, then writes something different aside, then delivers it to the destination, then this is a failed communication because there's no accuracy into that. Okay. After that, you want the delivery of those messages to be timeless. Sometimes you need information in a specific time. After this time, this information is completely worthless. Okay, so this is another criteria. And finally, we have the jitter, which is the difference between the delays of each message. For example, if you have a television, you want every frame that you see, you want every frame to come with similar delay. Otherwise, you are going to have different quality depending on when you watch the image, right? So the quality is not going to be even. So you want to have the right jitter, which means that you want even delay between the delivery of the different messages. Okay? Okay. So before jumping into the different links and topologies, let's first talk a little bit about what are the different types of data that we can send and receive. So those are right here. Okay. So for example, the first one is the text. And here I have a question for you, right? So inside the computers, how is the text represented? Binary. Okay, yes. So it is true, every type of data needs to be represented in a binary way, so computers understand it, right? Okay, so text needs to be converted to binary data, and this is how we can receive it, right? Okay, so how about the numbers? They also need to be converted into the binary data, right? Okay, so for example, the text, if let's say the character A, the letter A, if I want to convert it into binary, what technology am I going to use? What do you think? Say again? Yeah, exactly. So we're going to use Unicode, the ACI. Yeah, exactly. So what is that? So let's say every character, or for all the characters, we have certain amount of bits that can represent all the characters. So if in the alphabet they were just 2 characters, how many bits do we need to represent those? 2 bits? Okay. Sorry? How many? 2?
8 bits.
8 bits? So we have 2 characters in the alphabet. How many bits do we need? 16? Okay, we're increasing the number. Any other suggestions? How many? 16?
24.
24? Okay. So just to remind you, we have 2 characters in the alphabet, no more than this. How many bits do we need? Any other suggestions? Okay. Well, in fact, we need only 1 bit. Why is that? Because if you have the letters A and B, you need 1 bit. 0 is going to be A and 1 is going to be B, right? So 1 bit that can be either 0 or 1 is going to point to either A or B. Since in the alphabet there are a lot of characters, and also the computers, they don't only use the alphabet, but they also want to display some symbols, okay? We are displaying those symbols with, of course, larger amount of bits. So this is how the text is displayed. Now, with the numbers, it's a little bit easier because you can directly convert numbers from one numeric system to another. So, for example, it is very easy to represent the number 10 into a binary system. You're just going to write it in binary and you're going to convert it directly, which is even easier. So we can say that converting numbers inside computers is way easier comparing to converting the other types of data. Okay? Now, let's talk about images. So, how are images processed by computers? Any ideas?
Pixel.
Yes, exactly. So, they have pixels, okay? So, I can give another question here. We have an image that is using just the black and the white colors, okay? How many bits do we need to represent each pixel? So imagine you have an image, right? And this image have different pixels, different squares, right? Every square can be either black or white. So each pixel can be either black or white. These are the only colors we have. How many bits do we need to represent each pixel? Any ideas? Don't be shy, guys. Try to guess. I'm not grading you on the questions I'm asking in the class, so you can say whatever you want. Even if you tell me apple, it's okay. Okay? So any ideas? Over there? There?
Two.
2 bits? Okay. Other ideas? Come on, guys. Over there? 1 bit? Okay. Other guesses? Okay. Why 1 bit? Say again, yeah.
It's like it goes with 8 bytes with, so
Okay.
it's kind of like
I mean, you're right. Yes, it is 1 bit. Exactly. So 0 is black, 1 is white. Pretty simple. So if we have, let's say, black, white, and 2 different shades of gray, so we can have like a little bit more shadows and things like this, then how many bits are we going? So if we have 4 colors per pixel, how many bits we need? 2 bits, yes. Yes, exactly. So 2 bits, each bit can be 0 or 1, so you have 4 possible combinations. And this is really how we are building images, right? So you have the colors encoded inside the computer, okay? And each color is represented by a different combination of bits. This is how we do images, okay? The audio, so the audio signal is normally a wave, okay? So you can imagine a wave traveling, and reaching some location. So normally you can convert, so when it's a wave, this is an analog signal, right? Because, so if the signal is on different steps, it's digital. If it's continuous, this is an analog signal. So you can convert this analog signal to a digital, and then each step you can represent again by bit, okay? Of course, we're going to go in a little bit more detail on those, but I just want you to have some idea. And finally, the video, we're not going to talk too much about videos because they are simply combinations between images and audio. So the video have different frames, and each of that frame, it's okay. Each of those frames represents a picture, which each picture has pixels, right? So this is how it works. Okay. Now, after we know the data that can travel, okay, here is the types of data. Now, what are the different types of travel, right? How we can transmit this data? Well, as you can see here, there are a few ways, okay? So there are simplex, half duplex, and full duplex. Okay, so simplex is just communication in one way. Okay, so for example, let's say I'm speaking to you, and let's say you don't have the ability to speak to me, then this is a simplex communication. Now, what is an example of a simplex communication? Can you think of anything? Yeah, so yeah, it's going just one way, right? So, any ideas for a real life example? Walkie-talkie? I'm gonna get later to the walkie-talkies. We're gonna talk about it a little in a bit. Remember that. Yes? A radio? Yes, a radio, you can hear it, but you cannot send anything. Yeah, exactly. Or for example, when you connect your keyboard to the computer, right? You can send something to the computer, but the computer doesn't send anything to the keyboard, correct? Yeah? Okay, now let's talk about the walkie-talkies. This is very interesting. So this is a great example of half-duplex communication. So what that means? Imagine a road, okay, that has only one line, okay? So when there is car on this road, no other car can go in the opposite direction, right? The car needs to wait first, and then it can go. So even though this road allows cars in both directions, they cannot go in both directions at the same time. And this is what it happens. So you have some link between those two devices, and when one device is sending data, the other one cannot send data. Or if it wants to send data, this data has to wait before being sent. And a great example of that is walkie-talkies. So in walkie-talkies, let's say I have a walkie-talkie and you have one, right? When I speak, can you speak? No. We cannot speak at the same time. I need to press the button and then I speak to you. Okay, then you hear the message, and after that, you can also press it and you can speak with me. Okay? So this is a great example of half duplex. And full duplex is, for example, how we're talking these days with our cell phones. Let's say if you have a communication on WhatsApp, if you have a call there, because you can both see each other, so the messages for the video are getting transferred at the same time. And also, when you speak, you can speak together, right? You don't need to wait for the other person to finish talking. Even our communication right here is full duplex, because while I speak, you can actually interrupt me and we can speak at the same time, right? So those are the different types of data flow. Okay. Okay. So now let's see the different elements of a network. Okay, real elements of a network. So first of all, so actually you have two main components. You have hosts, and then you have connection devices. Okay, so the host is normally a laptop, so this is something that can either send or receive messages. Okay, then we also have other types of devices that are helping for the network to work properly, right? So we have the modem, which connects a network to another network. Okay, we have switches, okay, that can allocate traffic between different devices. So in a switch, we're having multiple links, so we can switch between those links. Okay, and finally, we have the router, which, you know, it spreads the signal, so our devices into a local network can communicate with each other. And we're really going to see each of those devices, how they work and their importance inside every network. Okay? Okay. So now, what are the different criteria so we can actually justify whether the network is fast or slow? Is it working properly? Is it reliable? Is it not reliable? So those criteria are, first of all, performance, okay, which is measured, as you can see, with the transit time and the response time. Transit time is how long it takes for a message to be delivered to a destination, while the response time is how long does it take for a response to that message to come back. So maybe you know from your other classes, even if you don't, you're going to learn it here. Let's say when we want to access internet, what we're doing a request to a server, okay, and then the server is giving us a response with specific resources. So for example, if you want to access a website, okay, you type the URL to the website, so you send a request to the server, and then the server is giving you the response with the website, and you see it in your browser. Okay, so the transit time, so the time that it takes for you to request it and the time it takes for you to get it, are those important times that define how good is your network performing. Okay? Then the network reliability is measuring how frequently we're getting errors or how frequently your network gets slow. For example, if your home internet is fast for 1 hour, but then in the rest of the time it doesn't work, you definitely don't want this type of internet, right, at your home. So we're going to talk about this as well. And finally, which this is probably the most important topic about networks, is the network security. So how do we secure the network? How do we make sure that when I want to send a message to somebody over the network, that nobody else around the world can have it? Or how do I make sure that in my local network, if I want to get a message from a website or if I log in somewhere, how do I make sure that nobody else intercepts this message, right? These days, this sort of happens on the background. You don't think about it, but for example, if you use Wi-Fi, the message gets transmitted through the air, right? So it makes sense that somebody else can get the same message. You just grab it from there, you take it and you read it. So what and how can we prevent that? This is also a very interesting topic. All right, so normally when you want to connect two devices, you need to have a link. So the medium between two devices, okay, is called a link. You can imagine the link as a cable between computer A and computer B. Okay, and actually if it is a cable between computer A and computer B, this is actually a very secured way, because if you don't have access to what's inside the cable, there is no way that somebody else gets the message. And there are a few types of links. So here is a point-to-point connection, which is what I just described. And there is also multi-point connection, where you have one link, but at the same time, multiple devices are connected to that link. Okay, so that makes the link more useful. If multiple devices want to communicate, they don't need different links between each device. Okay. Okay. So as I said, link is what connects two or more devices together. When we have multiple links, then we have topology. Okay, so this means multiple devices and multiple links connected together. So more than one link makes a topology. Okay, and the first topology that was ever created, this is the mesh topology. Okay, so mesh topology is, if you have, let's say, 5 devices, you create a link between each of those devices. So device 1 is connected, it has 4 links going out of it to the other 4 devices. Device 2 does the same thing. So every device has a dedicated link between itself and the others. Okay? So I would ask you, what are the benefits of that? What do you think? Say again. So the positives are? What are the positives? Okay. Yes. 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 Yeah, so exactly, if we have, let's say, way more than 5 systems, which is the case today, it's going to be way more difficult, right? Okay, so as you mentioned, yeah, the positives are that there is faster exchange of data. Also, another very good positive thing is that if I cut this link right here, I don't do anything to the network, right? So I just stop the communication between those two devices, but the rest of them, they can exchange information as much as they want. Okay, this is a great thing. Now the negative things, one of them is, for example, if I have 1,000 computers and I want those computers to communicate, there are 2 problems that are coming into play. the first problem, which is a big problem, but is nothing compared to the other one. So the first problem is that I will need tons and tons of cables to pass between the computers. So imagine if I have 1,000 computers, of every computer are going 999 connections. Imagine so we need 999,000 cables, right? Which is crazy. And the even worst issue is that every computer need to have 1,000 ports, right? I told you that this is even worse. Imagine every computer is going to have 1,000 ports. That's impossible. Okay. So let's see what can be done in order to resolve this. Obviously, the mesh topology can be used for very, very small amount of devices. So another type of topology that actually solves the problems that I just mentioned is the star topology. And this is really how you're using internet most of the time at home. So I know people are using it using Wi-Fi, and we're going to talk about Wi-Fi, but let's imagine we're just using those links, okay? So now, we removed 998,000 cables doing this, right? This is because now from every computer I need just a single link to the hub, and then the hub is going to get the message from this computer. This message will have the address of the computer that we want to deliver the message, and then the message will get delivered. Another advantage is that now I only need one port, right? Which is way better comparing to the 1,000 that we needed before. And this is great, right? So also the security is not that bad as well, because the reliability, because if I cut a cable right here, the rest of the devices, they can still communicate, right? Okay, so now there are two major issues with the hub. One of it, I said it, it's that there is no dedicated link between the devices. Everything passes through the hub. So this means if we find a way with another device to get information that is meant not for us but for somebody else, we might be able to intercept it, okay? And can you think of any other disadvantages? Like there is one very big one. Yeah, actually, what I mean is very close to what you're saying. Yeah, if somebody is able to hack the hub, then he can have access to the messages, or what they can do is they can break the hub, right? So this means this system is very reliable on the single hub. You can think of it as your internet at home. If your router goes down, the whole internet in your home gets down, right? There is no question about it. So this is a very big disadvantage. Okay, then we have the bus topology, which I've actually seen in many factories. For example, if you're a big manufacturer and you want internet on the different lines, and you want this internet to be, let's say, with cable, you don't want Wi-Fi, right? So it's more reliable. What you can do is you can pretty much pass a cable throughout the whole factory, okay, everywhere, and then do those top lines. So from this cable that you passed, you can do a top line, so another cable that goes down, and then you can connect different devices at this particular station. That way, all the computers in the factory, they can communicate between each other, and this is how you can build a private network. Okay? The disadvantage of that strategy is that you cannot do infinitely long cable, because when you are transmitting signals, some of the energy to transmit the signals is always transferred into heat. So with the time, you're going to lose the signal more and more and more, and you cannot do infinitely long cable for this reason. Okay. And then we have the ring topology. And this is an interesting one because here every device has a repeater and every device is connected with two other devices. Okay, so we have a link from this one to that one and from this one to that one and so on. So what it happens if I want to send a message from this device to that one? This device is going to send a message to this computer. This computer is going to firstly repeat the signal so the signal doesn't lose its strength. Okay, it's going to send the message here, then it's going to drop the message, right? Then the message will go there, and we're going to access the message from the computer that we would like to. There could be a lot of disadvantages with that topology. So can you think of some disadvantages? Yeah. Yes, yes, it can be a lot of time, true. It, it, yes, yes, yes. So yeah, every computer has to process the information, which is not optimal. Also, another disadvantage would be if this device goes down, there is nothing here to repeat the message, right? So we're just gonna cut everything, and if I want to deliver the message, either I should go the other way, or from this way it's not gonna work. But how about if this and that devices go down, then this one gets completely isolated, right? All right. So now, once we know the basics, we know the different topologies, you know, now we can actually start talking about networks, okay? So the first network I'm going to show you, okay, that's good. So the first network I'm going to show you is the local area network, or WAN, okay? So the local area network, it is called local for a reason, and this is because normally you expect a local area network, let's say at your home, inside the university. So all the devices in the university, even though there are so many rooms, this is also a local area network, right? Multiple devices locally that can communicate with each other. Normally, a local area network has a single external IP address with which it communicates to all the rest of the networks in the internet. So let's say a message from the internet comes, it reaches the local area network IP, okay? Then this message goes inside the network translates the external IP to internal one and delivers it to a specific computer. In the same way, this happens at your home. So no matter how many devices you have at your home, you have only one IP address. Do we agree on that? Yeah? So you have one IP address with which you access internet, but multiple devices can be connected to your network. So it works in the same way. When a message comes, goes to your network, and then the network finds the local IP address of your device. But of course, we're going to talk about this in more detail. You can see that the different topologies can be implemented here. So you can have a single cable that has all the hosts connected, or you can also connect all the devices together, the star topology, and to do that you can use switch. Okay, so you connect every device into switch, and then they can communicate between each other. So guys, have you ever seen how a switch looks like? Because you've definitely seen a router, because you have it at home, but have you seen a switch? How it looks? Any of you? Okay, let me show you a switch so you know how it looks. Okay, so this is how a switch looks like. If you heard of Cisco, they are making most of the switches these days. So it is a very simple thing. You just have some Ethernet ports, right? And then you connect each device to those ports. That way you can create a local network between those devices so they can interact between themselves, okay? So with the switch, you can also connect a router. So let's say if you have a laptop, you connect to the router, and the router can give you connection through the switch to all the devices that you want to use. Okay. So yeah, if you haven't seen, it's a very simple device. So at least now when I say switch, you can imagine this picture. Okay. All right, so we now know what is local area network, okay? So now let's talk about the wide area network. So with very simple words, the wide area network is connection between different networks, okay? So let's say if there is an office in Fitchburg and there is another in Boston, they have local area networks. When we connect them, now we have a wide area network, right? So here I put this table so you can actually see the differences if you want to read it yourself, right? So obviously the size of the wide area network is bigger. The wide area network covers a way bigger area, okay? And you can see that the one connects devices while the wide area network connects connecting devices. So local area network connects computers, wide area network connects routers. Okay. Okay, and here you can see a very simple picture on how this is done. So there's one network here, another network here. You can imagine this as passing a cable between those two networks, and here's how they get connected together. Okay, so this is one way. Another way is by using switches. So the device that I just showed you. Okay, so let's say you can have a switch here and here, right? And to those switches you can connect multiple networks. Okay, so the cable that is the output cable of the network. So you imagine your router at home, right? You can connect the cable to your router, which will give access to your whole network. And actually this is how you connect to the internet, right? You have one cable that goes in, this cable goes somewhere else, nobody knows where, somewhere under the ground, and it disappears. So what's happening with this cable? It goes under the ground, it goes to the internet provider, okay? It goes to a switch, and there are multiple switches with cables from different areas, and this is how they can get connected with each other. And this is how also they can stop your internet, because they just need to disable the port with which you're connected to their switch, and this is how your internet actually stops. It's pretty simple. Okay, and this is actually displayed here very simple. So let's say we have an office on the West Coast and we have office on the East Coast. Okay, so in this office we have multiple laptops that are connected to a router, and we have a router at the East Coast as well. After that, we do a point-to-point connection, so we do a cable between them, which would be a very long cable, as you can imagine. And this is how they can exchange information between themselves. Of course, these days, this is not done with one long cable. We're doing other things in order to connect different networks, but I'll explain you in a second how it works. Okay? And by the way, when we connect two networks, then we're having an internet, right? So this is why we use the word internet, which is connecting to networks, and the internet is what we're all using these days as a place that is consistent of multiple networks that are connected together. Okay, so we talked already about switching and how we connect devices together using switches, okay? But there are two very important types of switching that we need to talk about. Actually, they are really the backbone of the internet today, okay? So there is circuit switching and then packet switching. So I will explain you how circuit switching works, and then I'm going to ask you about packet switching to see what you're thinking about it, okay? Okay, so in circuit switching, you can imagine that we're having two networks. Let's say in those networks we have only phones, okay? So not only computers, they can get connected. Actually, before we were using computers, the networks all around the world were to connect phones, right? So let's say we have one network of phones connected to each other, and another network of phones connected to each other through a switch. So this means that here every phone can speak with each other, but also because of this cable here, each phone off here can speak with each phone right here. So now, there is one problem that really comes up when we want to do that. Now, this link here, okay, this link needs to be able to support 4 phones talking from one side with four phones on the other side. So it needs to have the capacity to support 4 phones speaking with each other at the same time, right? It needs to support 4 pairs. So this means that if all 4 phones from one side talk with all 4 phones from the other side, then we use the full capacity of the link. Okay, so for us is the most worth it if this thing happens. However, this doesn't happen all the time, right? So maybe most of the time we're going to have only 2 pairs of phones speaking with each other. This means that we're wasting the link. So there is half of the capacity of the link that is never used. So the provider, they spend money for the link, but they don't use its full capacity, so they're losing money because of that, which is a problem, right? Now, in the packet switching, we are going to try to overcome this, okay? So now here, instead of connecting the devices directly, okay, with this link here, so here what we were doing is once we start communication, this phone with that phone, they're connected directly and they're just speaking straight away, okay, no time is lost. Now, here, instead of having a link with such a high capacity, what we're going to do is we're going to put a link that can support, in that case, 2 computers communicating with each other, okay? So if the link is supporting only 2 computers communicating with each other, no more than this, how can we have 4 computers connected at the same time here? And how we can have 4 computers on the other side? Let's say if all 4 computers from this side want to communicate with all 4 computers on that side, how can we achieve that? Any suggestions? Yes. Yes, yeah. So instead of having direct communication between the computers, okay, what we're going to do is every data that we want to send from one computer, we're going to put it in a packet. And a packet is a separate entity, okay? And we're going to shoot this packet through the cable. So in that case, if 2 computers are communicating with 2 computers on the other side, no time will be lost because we have enough capacity to send the packets as fast as possible, right? We have the capacity of the link. However, sorry?
But there is a high chance to get miscommunication over that, right?
With the packets, yes, of course, because packets can be lost along the way, right? So, yeah, it can be because here you don't connect the devices directly, so you don't need to make sure there is connection between the devices, but you're just sending the packet there. You have the address of the device that you want to get, right? And you're hoping this packet to receive it. We're going to talk about this when we talk about the transport layer later. But yeah, so let's say if you want to use all the devices on one side and on the other one, there is just going to be a delay. So if you want to use all devices, then there is going to be a queue with those packets that are waiting to be sent, just because the link doesn't have enough capacity to send messages from all of the 4 computers. Okay, and in that way you are saying, okay, I'm going to introduce a delay if there is high traffic, okay, in order to make sure that this link is always utilized correctly and on maximum, right? So we always use the max capacity of the link. And this is why sometimes if in your local network too many people are connected to the internet, what's going to happen is that your internet will get slower. Why is it going to get slower? Because there will be a lot of packets that are waiting for you to send to the internet, simply because the link that you have doesn't have enough capacity to support all the packets going together. Now, as you can see here, this is a representation of the internet, how it works these days, right? So as you can see, we're jumping from the way two devices communicate, what are links, what are local area networks, what is wide area network, and now we can build even higher on discussing what the internet is, right? So the internet works in a very simple way. So first of all, we have here networks called backbones. So you can imagine this is a network of different switches and connection devices, okay? And those are owned by the internet service providers. Those are AT&T, actually this is the only one I know in US. Can you think of, Verizon, yes, yes, yes. What was it, another one? Okay, yeah, Verizon, Xfinity, yeah. Yes, yes, exactly. So those are the people that own the backbones, okay? And of course, they make an agreement because in different states, they are different providers. So they make an agreement so they can use their devices, okay? Now, after them, through pairing points, which is, you can imagine, again, a more local building with switches and connection devices and routers and so on, we have a local provider network, okay? So we move from this big web of backbones and we go to a local provider. So what is happening, for example, if we have some smaller internet provider, let's say AT&T, is selling to this local provider access to their network. So the local provider is paying fee to AT&T, and finally this local provider is delivering the network to the customer, which is paying even higher fee comparing to them, okay? And finally the customer can use the internet. So let's say if this person wants to send a message to that person, it will go through the local provider, then it will go through the backbones, which is the connection of switches and routers. It will find the best way using algorithms in order to find the shortest path. So have you learned about shortest path algorithms, right? When you're trying to find a way between different nodes. So there are many algorithms that I know we're studying them in Fitchburg about how to find the shortest path from one place to another one. Those type of algorithms are used to search how to find the shortest path from one customer to another, right? To which router should I go next? To which switch should I go next? Which link is currently not busy, okay? So using those algorithms, you can put different weights on the different switches and routers, and this is how you can find the shortest path to the destination through the internet. So that's why in the computer science classes, we're studying those things because they have a lot of practical applications in networks. Okay, so those are just different ways with which a network is established, right? So as I already mentioned, we're using the telephone network, which is in most of the cases. So as I said, before the internet, there were just phones. So when the internet was built, we decided to use the phone networks in order to connect devices through the internet, right? We can also use cable network. So this is what we use for the TV. We can use Wi-Fi, which is what we use at home. And also we can do direct connection to the internet that most of the big companies are doing, right? So I assume also the university is connected directly to the backbones, right? And this is how they are using internet, especially for, as I said, big companies and corporations. Okay, so now, once we know the different types of networks, now we can start speaking about protocols, right? And what are the rules when we want to exchange information. So I will give you an example with Maria and Anne, okay? Or we can even give an example with you speaking with your friend. So as I said, when you speak with your friend and you're in the same room, we can say that we have only one layer connection. So we need only one layer to do this type of communication. Maria can do two functions. She can listen and she can talk, okay? Then we're going to use air as medium so they can deliver the messages, and also Anne can also listen and talk, okay? So we can say that at the same layer, okay, we can do two opposite tasks in order to communicate. But what happens if Anne and Maria are on different sides of the world, okay? How this changes. Also, we should think about how Maria and Anne interact between each other. So are there some rules into their communication? So obviously, if they are friends and they know each other, they don't need to speak in official way. It's not like how we're speaking together, right? Because if they are very close friends, they might use some type of dictionary. Here, we're using different type of dictionary, okay? Also, it is important to know that when they meet, they always know to say, for example, hey, how are you? Good morning, right? And when they separate each other, when they finish the conversation, they are saying, okay, bye, have a good evening, right? So those are some rules that we all use in our communication. And as I told you, when we're communicating through the internet, we use exactly the same rules because everything comes from the basics of human communication. So let's see if they are located very far from each other. What's happening there? Okay. So now they're located in different offices. And then the things are becoming a little bit more complicated, right? We need a little bit more layers in order for them to communicate with each other. So in that case, even if Maria can listen and talk, Anne will not be able to hear her, right? So we need to divide this into layers. The first layer, or actually here is the third layer, is going to be listen and talk. The second layer is going to be encryption, decryption. So let's say Maria will talk, then in the third layer, her words are going to pass through certain machine and they're going to become a plain text, okay? So they're just going to be written on a piece of paper as they are. Then, in order for nobody else to be able to read that, we're going to pass a second layer where we're going to convert the plain text. So we're going to pass it through some machine, okay? And we're going to convert the plain text into ciphertext or something that's encrypted and that nobody can understand how it works and nobody can read. And finally, once it's encrypted, what's the next stage? To what? Sorry? To mail it, yeah. Exactly. We need to deliver it, right? And then we're going to pass it through another machine that is actually going to be responsible to deliver the mail. Okay? So once it passes this machine, it will get delivered, of course, and after that, on N side, the text will be received, decrypted, okay, and then she's going to be able to read it. Now, why do we need to have 3 different machines for each task? Why don't we just have one machine that is doing everything all together? Isn't it like way more simple? Why am I even explaining you like so many like layer 3 and there are even more layers in networking? Why do we need to do that? What do you think? More secure? Okay, good. Anything else? So, okay, let's say, I'll give you an example. Let's say if layer 2 breaks, okay? If the decryption breaks, what's going to happen? We need to replace the decryption machine, right? Okay, so if everything is all together, the one machine that is doing everything breaks. We don't know where the problem is, just the communication breaks. We don't know if it's in the encryption, we don't know if it's listen, talk, we don't know if it's in the delivery. We know it's somewhere in the machine. So we need to separate communication in layers. So if something breaks, we know it in which layer this thing happened. So after that, we can replace this layer or improve it. If we have everything in one place, then it's going to be way more difficult to detect issues and actually way more difficult to build the layers because we need to build everything on the same place. Okay, so yeah, this is why we need to break it down to layers. Okay, so when we are working with layers, there are 2 main rules. Okay, so the first rule is that we at every layer we need to do 2 opposite tasks, right? Which is talk, listen, send, receive, okay? And the other one is encrypt, decrypt. This is the first rule in order to have a layer. The second rule is that every layer should work with the same object, right? So let's say I'll show you in the figure before. Actually, let's see here. So let's say at layer 3, we have plain text, right? We have plain text here and we have plain text here. So every layer should work with the same object, okay? And even though that the message doesn't go directly from here to here, right? It needs to go from the third to the second to the first, get mailed, and go up here. When we want to build the different layers, we can say that at layer 3, we have logical connection between layer 3 at Maria and layer 3 at Anne. Why is that? I'll give you an example. So with your computers, when you want to connect to the internet, 2 applications are communicating in the application layer. So we need to think of the messages sent between application 1 and 2 as application level messages, okay, that are getting transferred only in the application layer. We don't want to think about everything that is happening under the application layer, right? When we want to build applications, you don't want to think about how the messages are getting transferred into bits from the cable, right? You don't want to care about this. You want to care only what's happening at this type of layer. That's why we can say that at each side, the layers have logical connection between themselves. Okay? Okay, so as I mentioned, when we're communicating with each other, we're using some protocol on how we're going to speak with each other, right? So when you send messages through the internet, we also have a protocol because we want to make sure that all the devices understand each other, okay? And the protocol that is used today is the TCP IP protocol. So I have a question for you guys. First of all, do you know what is TCP? Any ideas? Transmission, transport, I hear something like this. Of course. Now you're going to refresh. How? Transmission? Close, not exactly.
Transport.
Yeah, transport. But yeah, it's a similar thing. So TCP is transport protocol, right? And IP, what is IP? Exactly. Yeah. Okay, we all know that, right? Okay. So why this protocol is protocol suite? This why it's called protocol suite, because it involves many protocols, right? But the most important ones are at the transport layer and IP, which is at the network layer. That's why it is called like this. This involves all the sets of protocols in which we're communicating on every layer when communicating from a computer to another one or to the internet. Okay? And this is a type of the protocol that we're going to learn here. Okay? So actually the protocol suite, I should say, because for example the IP is the protocol in the network layer. Okay? So yeah, we're going to talk about all of those protocols in the upcoming lectures. Okay, and finally, it is worth mentioning the different layers that are involved in communication and about which we're going to take a focus in each and every layer. Okay, so as I said, on the very top, okay, is what your applications are using, the final result that you get. This is the application layer. Then you get the transport. Under it is the network layer, the data link layer that connects the devices, and finally you have the physical layer. Okay, so let's see each of those layers, how they work together. Okay, now in real life, if I want to send a message from a computer to another one, in the same way how I explain you the situation where two friends are talking from distance, okay, this is something similar, okay. So you can imagine that from the application, you know, the message gets to the transport, to the network, data link, physical, then gets transferred, okay, and at some point it reaches a destination and it again gets to the application layer, okay. Now, it's important to say that as you can see, the physical and the data link layer, okay, they are valid from, so you can say of each of those hop, right? So the source is one hop, then the switch is another hop, router is a third hop, another hop, and so on. And the source and the destination, okay, are the two hosts, okay. So we can say the application layer is host to host, transport host to host, network, it's also host to host, but as you can see in the routers, we're doing something here with the network layer, which I will tell you about. And the data link and the physical, they're hop to hop. What that means? That means that the message in the physical layer, when it reaches the switch, it might change, okay? And when it reaches the data link layer here, the message here might change too, okay? Then it will go through here. However, even the data link part of the message changes, the rest of the parts, they're not going to change. And if that sounds confusing, we're going to talk exactly how this works, okay? So let me see if I have a better representation and I'll explain it very easily. Okay, so how that works. Now, let's say, okay, let's imagine a real life situation, right? You want to send a message in WhatsApp to your friend, okay? And you're sending the text. So the text is what goes in the application layer, Okay, so we have the text in the application layer. After that, in order for this message to be transported, okay, we put the message in a transport layer, so we add something here on the top. We call it the transport layer header. So let's say the message image on the text, and on the top of it, I put some information, okay, that is going to say with what protocol this message is going to be transported. Okay, so the message I want to send is still here, okay, it's just on the top I put some additional information. Okay, after that, when we go in the network layer, I again encapsulate everything, so the message and the transport layer information, I encapsulate it, and then on the top I put the network layer information. What's the network layer information? Mainly the IP address, okay? In the transport layer, I put the port in which I want my message to go, okay? So we have the message, hey, how are you? We put the port on the top, yeah? Then we put the IP, okay? After that, on the data link, we put the MAC address, okay? So this is of the devices, so we know now the specific device, because the IP address is going to give us the network, right? In a network, there can be multiple devices, right? So data link layer is going to give us the exact link where we need to deliver the message. And after that, we're gonna pass this message, and we're gonna make it in bits, so we can actually transmit it to cable, through the cable or through the air. We are saying bits, but actually when we transmit it to the cable, we actually, from these bits, we create a signal, okay? So you can imagine we want to transport the bits 0 and 1, we transport the signal, okay? So this is 0, this is 1, okay? We transport the signal, and the device that reads it, it says, okay, this is 0, this is 1, okay, I know what it means. Let's convert it to zeros and ones, and then let's start to read the message from bottom up. Sure, yeah. So why do I say that the physical and the data link layer are from hop to hop? Well, this is because the cable between the host and the router, or between the host and the switch, okay, might be different, might have different capacity, okay? So that's why the information in the physical layer here, okay, it might be slightly different, right? Depending on where we want to go, okay? So when we go to the router, then some of the bits are going to change, right? Because we reach the destination of the router, now we want to move to the next destination, so we're going to change some bits on where we want to go. The data link layer also is hop to hop, because firstly we want to deliver the message to the router port, not to the computer port of the destination. So in the data link layer, we're going to say what is the place, what is the link through which we want to send the message, okay? That is going to go to the router, okay? And once we go to the router, why in the router we also open the message in the network layer? Well, this is because sometimes if in the next link we have different rules or different type of protocol, okay, sometimes we want to break the message into smaller parts, okay? So what is the router doing in the network layer? The message can get opened, get into smaller parts. On each part we're again going to put the same IP and then move it down through the rest of the layers, okay? In the routers and the switches, we have no transport layer, okay? We have no ports in terms of applications. We also don't have application program that is going to read our message, right? In the router, you don't expect to have WhatsApp, and in the switch as well. So that's why those connections with the transport and application layer, they're logical with the destination host, okay? Okay. So yeah, as I mentioned, in the application layer, we use names. So whatever is the message, it can be a custom one, depending on what applications we use. In the transport layer, we use port numbers, network layer, logical addresses, which is the IP, okay? In the data link layer, we use the address of the link through which we're transferring the message, okay? And in the physical layer, we're just using bits, okay, or signals. Okay. Okay. And now, finally, I just want to mention that the fact that we're talking about how a single message is transmitted, this doesn't mean that the messages are always getting transmitted one by one, right? So, for example, you can multiplex messages. Let's say the protocols that are in the application layer are FTP, HTTP, SMTP. Do you know some of those protocols, what they do? Have you seen them? FTP? Any ideas? How? No, not exactly. Yeah, okay. So FTP are the rules on how a file gets transferred from one application to another. HTTP, the most popular. So HTTP is a protocol that is used to access websites, right? So you're writing HTTP and then the website. And these days we also have HTTPS. Do you know why we need S? Do you know what it stands for? Exactly, true, yes. So the S, right, comes from the security protocol, which is added on the top of the HTTP, so your information can actually get encrypted, especially if you put credit card information or other personal data. Okay, SNMP, any ideas? So, sorry?
Simple network.
Simple network, yeah, close, yeah. So yeah, this is when you want to network to establish network with different devices, right? SNMP. Okay, so what this picture represents is that multiple application layer protocols and messages can be encapsulated together in a single TCP packet, okay? So let's say your application wants to send like one file transfer, one access to the internet, right? It can encapsulate this in a single TCP packet, okay? And multiple TCP packets or UDP packets, which is on the transport level, they can get encapsulated into IP, right? Into the network protocol and get sent all together. Questions? What is the TCP and the UDP protocol, and what's the difference between them? Any ideas? So TCP and UDP are protocols on the network layer, okay? And
User data protocol, it's like personal for the personal use.
good guess, good guess.
Like for the personal communication or like personal protocol.
Okay, okay. We use UDP, it's true. Usually when we're, let's say on video calls, we're using UDP, okay. But any other differences between those? Any ideas?
UDP is faster for downloads.
Okay, UDP is faster.
And
Yeah.
then you need like very short memory.
Okay, so I would agree it's faster. I wouldn't agree that we use UDP for transfer of files and so on. But UDP is faster, yes. So here is the difference, okay? TCP is protocol that establishes connection with the receiver before transmitting the message, okay? We need to have some connection already established. So you can imagine that I'm connecting with somebody, we establish a logical connection, okay, between ourselves, and then I'm shooting messages. I know exactly where they go. Now, the UDP, you don't establish connection, which means, and we're talking for the application layer, which means that with UDP, you're not sure that what you're sending is received. Okay, with the TCP, you're 100% sure that what you're sending is received, and if it is not received, you know that it's not received, and you send it again. So TCP is always used with FTP. So if you want to transfer a file, you want to make sure that this file is in fact received, right? So if in TCP we're sure that what we sent is received, why do we even need UDP? And in what situations we're actually okay to send the data but not to be sure if it is received? What are those situations? Actually, I just mentioned one of those. This is when we do, this is when we do video calls. So in the video calls, you value way more to actually talk with the person rather than to have the best quality all the time. And you can see sometimes when you talk with the phone while driving a car, right? If you pass through a network with slower internet, like you're further from the cell, your call will start breaking down, but it's not going to stop. It's not going to hang unless you really don't have internet, right? So this is because when you have slower internet, some of the packets, they don't get received to you. You don't get them, right? And you can see that the quality of the call deteriorates, so it goes down. When you're with better connection, you receive more packets and you have better quality. But this is the advantage of the UDP. So first of all, of course, as you mentioned, it's faster, okay? It's connectionless, so you're not sure if you receive the data, but it will help you to keep whatever you're doing because it takes like way less space comparing to the TCP. So for things like video calls, it is very great. Yeah.
It's like watching TV.
Yes, it is UDP. Yeah. If you watch videos, it's the same thing, right? So yeah, exactly. Okay, so this was everything for today, guys. Any questions so far? I know it's been a lot of information, right? A lot of information, but think about the fact that today we're just summing up everything, and now we're going to get step by step each layer. We're going to look at it in a detail, and you're really going to dig into it like in a lot of detail. Okay? Questions? No questions? Okay, good. So you can read reference 1. It is actually, I think it's about, let me see. So it's only 30 pages. So everything I showed you is just in 30 pages. And it's like not very small typing, right? So you can really read it in your free time. I think it will take you about 1-2 hours max. So this is the only task I give you for the next week. I think it's fair, right? Okay, all right. Thanks everyone, and nice meeting you.